What does it mean to flip a coin and have a probability of 1/2 of getting a head and 1/2 of getting a tail? For every given coin flip that you ever make, you'll either get a head or you'll get a tail, but you're not going to get 50% of both. So what does that actually mean? Well, in the long run, if we keep flipping coins over and over and over again, roughly 50% of the coin flips will be head and 50% of the coin flips will be tail. But can we make that precise? I mean, what does it really mean? And that's what we'll be talking about today. We'll be doing the law of large numbers, the strong law, the weak law, and the strong law of large numbers. And this idea of if we repeat an experiment over and over and over again in an independent fashion, which may or may not be possible, and then leads to a whole philosophical debate as to whether it even makes sense to talk about long-run averages. That all being said, if we were to repeat an experiment over and over again in an independent way, the result should tend to the average, the mean. How can we make this more precise? Well, we're going to prove it. Yes, we're going to prove it. In today's lecture, we're going to prove the weak law of large number. It's very quick to do. Then we're going to prove the strong law of large number, and it's kind of a pain, but we're going to get through it using all of our tools at our disposal, including Chebyshev's inequality and the Borel-Cantelli lemmas. So, let's get into the notes. And welcome back to another lecture of probability and measure. Today we'll be talking about the one and only law of large numbers. And when I say one and only, I mean actually there's multiple different versions of the laws of large numbers. So it's really more of a plural thing than just a one. But it is a very fundamental result, something that you would probably learn the very first time you take a course in statistics or probability theory. The idea that, well, if I have a lot of random variables and I add them up and I divide by the total, I'm going to get something that's going to converge to the mean, assuming the mean exists. But we have to try to make that a little bit more precise and see how we can understand it in the context of measure theoretic probability. That's the goal of today's lecture. So let's just get right into that, shall we? All right, so what we're going to do is ultimately try to prove the strong law of large numbers, which is, well, stronger than the weak law of large numbers. But we're going to start with the weak law because it's super easy to prove, and it's something that we can use as just an idea of how we might then extend it to the strong law, which has much weaker conditions. It's a little confusing, right? Because the strong law has weaker assumptions and the weak law has stronger assumptions, but hence the strength difference. Anyway, we're going to need some formality for first, right? Because we're not just going to hand wave our way through this, we're going to be doing it like a good measure theory class. So what we'll say is let the collection xi, I from 1 to infinity, be, oh yes, random variables. I haven't discussed what independent means yet, so we're going to get there. Random variables from a measure space, omega f p, to some measurable, well, one of our favorite spaces, the real line with the Borel sigma field, the Borel sets. You could consider different settings, but this is kind of the most natural one when we think of real valued random variables. So I'll say hence, for any set A, any Borel set, we can ask what its probability is for a given x. So what we can say is that the probability that x is in A, well, what is that? Right? What we're doing is we have a measure, a probability measure p, but the probability measure p is over here in omega, whereas A is over here in the Borel sets. So what's going on here? What's going on is we're actually defining this. This is really just shorthand, something that we would see all the time in sort of less rigorous settings, but to define it precisely, right, what we're really saying is we want the measure of the set of omega such that x as a measurable function maps omega into A. Right, so what's really going on here is we have two spaces. Well, we have our measurable, or our measure space, our probability space, and then we have the real line. And what's happening, right, is if I have some set on the real line, say A, then X is going to inverse map that, or what I should say is there's going to be some corresponding set of omega, say, such that X is going to map those omega into A. This is the X map. So again, it's the way we're thinking about it here is that X, okay, I'm not sure how you think about random variables, but it's really a measurable function here from one measure space to the real line, I guess, with the Borel sigma field. But this allows us to write down some of the things that we're, familiar with, like an expected value. So we define the expected value, Ex, the expected value of X, to just be the integral of this function X omega dp. So it looks kind of exactly like what we would have done with integrals for measurable functions. We will also be very often using the notation Sn, and Sn is going to be the sum, I from 1 to n, of the first, basically it's the sum of the first n of the xi's. And this is also a measurable random variable. Recall, right, that if I have, 2 or 3 or n measurable functions, I can add those together. I still have a measurable function. Same idea for random variables. Remember, in this mindset, the best way to think about them is that a random variable x is just a measurable function that we're calling now a random variable because it's mapping from a probability space rather than just some arbitrary measure space. So before going forward, we also have to define what independent random variables mean in this context. So our definition for independence. Now recall, we did something kind of similar with independent collections of sets and independent sigma fields earlier in these lectures. But for random variables, right, we say that x and y on the same probability space. Otherwise, yeah, things can be a little bit funky, right? If we have two random variables on the same probability space, which once again we'll just call omega fp, we say but with possibly different codomains, so they don't have to map into the same space, right? Which we'll call, I think, my bold x and script x for my measurable space for the codomain of x, and similarly we'll have our space bold y and script y for the sigma field. So then, if you want them both to be the real line in the Borel sets, they can be, right? The point is they don't have to be. Then we say that x and y are independent if the probability of the intersection of x being in A and y being in B is equal to the product of the two probabilities. The product of x in A and y in B, and this is for all x, or for all A, sorry, A in the sigma field X and B in the sigma field Y. So this will look very similar to what we saw before when we had independent sets. And we just said, well, a collection of sets is independent, right? If the measure of the intersection is the product of the two measures. In this case, what we're doing is we're taking the A and B from the codomain, right? And we're mapping it back into the omega FP space. And then we're saying, well, what's the measure of all the omegas that get mapped into A by X and the omegas that get mapped into B by Y? And if those sets in omega as subsets of omega are independent for any A and B, then we have that our random variables, our measurable functions, are independent. Then we can say this can be extended to finite collections, let's say xi, I from 1 to n. And in that case, right, what we get with the condition that the probability of the intersection I from 1 to n of the sets xi in AI is equal to the product, right? So the intersection comes out and becomes a product, I from 1 to n, of the probability of xi in AI. Okay. And this is, I guess, also, I should say, for all AI, right? In whatever the space AIs are living in, right? Let's say they're all Borel sets, for example. So for any choice of AIs, then we can do this. And that's what independence means in this context. Now we can go one step further. This is for finite collections. We can say for, or not for, maybe. We'll say also, comma, the infinite collection of xi's is independent if every finite set of xi's is independent. So very similar to what we saw for sets and sigma fields, the same idea applies here for random variables. If we have an infinite collection of random variables, which we are going to have for the law of large numbers, we say that the entire collection is independent if for any finite subset, any finite x's that I pick out, that collection will have to be independent as per the previous definition. So that's how we kind of extend this. And yeah, I think I already talked about this shorthand. Yeah, I guess we can, note. Right. Since XA, as I mentioned, is really just saying it's really a subset of omega. It's all of the omega that get mapped by X into A, right? Which is also could be written as the inverse mapping of A. So there's different ways we can think of this set. I mean, it's all the same thing, of course, but right, we can think of X in A, or A being mapped back by X into omega. So since this is true, then X and Y are independent if and only if we have the sigma fields, sigma fields, sigma x and sigma y are independent. Independent. There we go. Get all the letters in there right before we run off the page. So yeah, this case, the idea being that x is going to map back a bunch of sets into omega, and that's going to be a sigma field, sigma x, and y is going to do the same thing, and those two sigma fields must be independent if x and y are independent, and vice versa. So it's all very closely related. In some sense, you can think of a random variable as, an induced sigma field over omega, right? In the sense that it's going to take the sigma field in the codomain space, like the Borel sets, and map them all back into some other sigma field. So we have a couple other things, right? Yeah, that's right. We need to talk about identically distributed is the next thing. So, because of course, if you've taken any course in probability or statistics, you would have heard the phrase independent and identically distributed. But then what in the world does that mean in this context? I mean, we know what we want it to mean, which is they have the same distribution function. What's a distribution function, right? The more you do this measure theoretic probability, the more you start to think, do I even understand anything about probability? Like, what in the world is a distribution function? What in the world is a measure? What's a random variable? Don't know anymore. Anyway, what we can say is that for x mapping omega into the reals, the distribution, or sometimes called the law, you'll see people talk about the law of a random variable or convergence in laws. So it's just, I don't think there's any difference between that and distribution, but it's just different terminology. Not sure exactly the origin of that. Maybe I should look it up, but yeah, save that for the future. So the distribution or law is the measure induced, get the n in there, induced by x on the reals. That is, so for example, i.e., we have for a Borel set, right? This is P, the measure. But remember, P is measuring sets in omega, so we can't measure A with P. But what we can do is we can map it back with X and then measure it. So in some sense, it's exactly what we already wrote. But it's good to try to see what's really going on here. Yeah, and basically, we say that x and y are identically distributed if measures p of x inverse a, or p of x inverse, and p of y inverse coincide almost everywhere. I'll just write AE for almost everywhere. Or almost surely, I guess. We're in probability now, so let's switch almost everywhere to almost surely. Right, so these are two different measures on the Borel sets on the real line. If they coincide, then we say that x and y are equal in distribution. If they coincide almost surely, so we can, mess around on a set of, I guess, measure 0. I guess in that case, what does that mean, right? Lebesgue measure 0, right? If I modify my Borel sets a little bit, I should be able to maintain the same Is that what I want? Yeah, what does it even mean to coincide almost surely? It doesn't mean Lebesgue sets because you could have a point mass in one that's not a point mass in the other, so that's not right. I mean, Lebesgue measure. Man, this stuff is just amazing, right? Yeah, I think what they mean by this is that, I guess on sets of measure 0 with respect to these measures, right, we can kind of, change things slightly. Yeah, and we say that if x and y are identically distributed, then we are automatically assuming that they have the same domain and codomain. Otherwise, it doesn't really make sense. They have to have the same distribution in the place they're mapping into. Anyway, given all of that definitions, we're already ready to state the weak law of large numbers. This is the baby version that assumes way too much. Weak law of large numbers. So the weak law of large numbers says in this context, let omega fp be a probability space. Good start. Xi, I from 1 to infinity, be random variables, from omega into the reals such that the expected value of xi is going to be c. Did I say that they're... Oh yeah, I guess we don't need that. It's going to be c in R, and this is for all I, and the expected value of xi squared is going to be 1, and this is for all I. 1 to infinity, right? Oh yes, and they are uncorrelated, which in this context, what we mean is that the expected value of the product of xi minus c, xj minus c, is going to equal 0. This is for all I not equal to j. Okay, so what do we have? Probability space, collection of random variables. They all have the same mean. They all have a second moment, x squared of 1, and they're all uncorrelated, which is a weaker condition than being independent. Then Sn, the sum of the first n of them, divided by n, converges to C, and it converges to C P, which is in probability. All right, so how do we do it? We use Chebyshev's inequality, and then we're basically done. The proof of the weak law of large numbers says, well, without loss of generality, we're going to assume that C is going to be 0. Otherwise, well, I'll just write it out. Otherwise, replace xi with xi minus c. So in that case, right, we can just assume c is 0. It's going to make our lives a little bit easier. Then, for any t greater than 0, Chebyshev says what? Chebyshev says that, well, the probability that the absolute value of the sum of the first n terms, Sn over n, divided by n, being greater than or equal to some epsilon, I guess I should say, for all epsilon greater than, or for any, yeah, we'll just say for epsilon greater than 0, So we have that, for whatever epsilon we want, the probability that this sum is greater than epsilon, well, Chebyshev says that's going to be less than or equal to the expected value of Sn squared divided by t. Oh, I think I switched my notation. That's why. For any t, that's why. That was a typo on my part. I was using t, not epsilon. So for any t greater than 0, right, the expected value here is going to be this divided by t squared divided by n squared. And, well, what's the numerator here? The numerator in this case is just going to be a double sum, I, j, from 1 to n, of the expected value of xi, xj. The product there. And then, of course, in the denominator, we still have a t squared, n squared. And, well, what's that numerator? Well, that numerator is just going to become n, because we have n squared things in our sum, but most of them are going to be 0 thanks to this uncorrelated condition. And the ones that aren't 0 are going to be 1, because we're assuming that they have a unit value for their second moment. Otherwise, well, we could just normalize to get some other constant out, but it's just easier to think of it this way. Anyway, this becomes n t squared, and no matter what t squared is positive, this thing's going to go to 0 as n goes to infinity. So no matter how small we make t, right, the probability that Sn over n is greater than t in the limit is going to go to 0. Hence, this is as n goes to infinity, and QED. That is, that's the weak law of large numbers. It's just Chebyshev's inequality, which says that in the limit, the probability that this thing is bigger than a small number is going to go to 0. So in a sense, Sn divided by n is going to tend towards 0, or for a non-zero mean c, it's going to tend to c. But we can do a lot better. In this case, we're assuming a finite second moment, a finite variance. We don't need to assume that, actually. And we can bump up our convergence. We started with convergence and probability here. We can bump it up to convergence almost surely, which is a stronger notion of convergence. So let's do that. But first, we need to define the variance. So in the next theorem, we require independence. We require independent xi's. So strictly speaking, it's not not all of the conditions are weakened. One condition is strengthened, which is we started in the weak law, assuming that everything is uncorrelated. For the strong law, we need to bump that up to independence, so it's a little bit, but everything else gets a little bit weakened. We also need the variance of a random variable, which we can define var of x, right? The variance of x is going to be the integral of x minus ex squared dp omega. I write it like that to remember that we're still in a measure theory world, right? Where x is a measurable function. The expected value of x is the integral of x over the entirety of omega with respect to the measure p. And the variance can look like this, but it is just the variance, the classic variance that you're probably used to from, well, vanilla statistics. And now we can state the strong law of large numbers. So the strong law of large numbers, this might actually be a short lecture compared to my 2-hour-long ones. Because all we need to do is prove this theorem. But I'll tell you right now, it's a little bit longer than the last one to prove. Spoiler alert. the strong law of large numbers. So in this case, we say let xi, I from 1 to infinity, be IID random variables from omega into r, just like last time. From omega to r. Now, if they're IID, so they all have the exact same mean, if the expected value, the expected value of the absolute value of xi is finite, so xi as a function is now integrable, absolutely integrable, then Sn divided by n is going to converge to C. Oh, that's right. I'll define it after that. Almost surely for C equal to the expected value of xi. Doesn't matter what the I is. Oh, and there's also a second part. This is the first. This is kind of the main part, but there is a second part. Also, if the expected value of the absolute value of x is infinity, then Sn over n does not converge to any finite limit. Maybe at the end of this we can fire up RStudio and watch this fail miserably for the Cauchy distribution, which does have infinite, I guess, if x had a Cauchy distribution, then the expected value, the absolute value of x would be infinity. The mean itself would just not exist because you'd be taking, I guess, infinity minus infinity, right? And that's never good. But yeah, so this is it. It basically says, so I just want to stare at this for a second, right? Specifically the first part. And the first part says that we have independent random variables, so a little bit stronger than being uncorrelated. But if you notice, we don't assume anything about the second moment. We just need the random variables to be absolutely integrable, L1, whatever you want to call them, right? Basically, we need this, the first moment, the first absolute moment to be finite. And then the sum over the sum, Sn divided by n, will converge almost surely. And the almost surely bit is also a stronger convergence criteria than what we had previously. So, well, first we're going to prove this part number 2. So we'll call this part number 2 and number 1. And for the proof, we'll do number 2 first, because it's kind of fast, right? And we're going to spend a lot more time doing the first bit. So let's argue by contradiction, right? Assume that the mean is infinite, but that this limit does exist. So we assume that n inverse Sn converges to some C, where C is a real number, not infinity. But also that the expected value of xi is going to be infinity. So it's kind of like saying if I divide infinity by n and n gets really big, does the thing go to a real number or not? In this case, no, you can't do that, but we'll see why. And then we note that x n divided by n is going to be Sn minus Sn minus 1, all divided by n. And this thing is going to have to go to 0. Why? Well, it's going to go to 0 in our assumption, because if we're assuming that this thing converges to C, then we're basically taking two things that can both converge to C, right, and then subtracting one from the other. Right, what we're saying is we're saying Sn over n minus Sn minus 1 over n, and this is going to converge to C minus C, which is going to be 0. So that's why that has to go to 0. This also is, if you're familiar with what a Cauchy sequence is, this is kind of like what we're getting at here. But we didn't really talk about that, and it's not really relevant for anything else we're doing, so I'm just going to ignore that right now. But yeah, it kind of might hint at something if you're familiar with some real analysis. Anyway, since the expected value of xi is assumed to be infinite, then the sum n from 0 to infinity of the probability that xi is greater than n is equal to infinity. You can show this if you want to, but I think somewhere it shows up in some of these. It shows up in these textbooks, like Dudley and Billingsley's textbooks, where they basically say if a random variable has a finite mean, then this sum has to converge, and if it has an infinite mean, or if the absolute moment is infinite in this case, then this sum has to diverge. So if we believe that's true, then Borel-Cantelli, which is going to be a major tool that we're using throughout this proof, well, Borel-Cantelli says that the absolute value of xn has to be greater than n for infinitely often, right? I'll just write IO so I don't have to spell that out and risk making a spelling mistake. Infinitely often for infinitely many n. What's that mean? Thus, the probability of the measure, right, of the set of omega in omega such that Sn minus 1 over n goes to 0, which, note, right, this thing is exactly xn over n, hence this box here. This measure is going to be 0. Therefore, n inverse Sn cannot converge to some real value. Does that seem clear, right? What we're basically saying is that, okay, if the expected value of the absolute value of xi is infinite, then these probabilities in this sum here, the sum n from 0 to infinity of p of xi goes to infinity, or is equal to infinity. Borel-Cantelli says that means that these events have to happen infinitely often, which means that for any omega, right, or I guess off of a set of measures 0, right, you're always going to eventually find an xn that takes a value bigger than n. So no matter how far I go out, I'll still find another one, which basically means that xn divided by n, this little thing I wrote in blue here, can't possibly go to 0 because there's always going to be some xn bigger than n out there. Again, in the limit, off of a set of measures 0, where we don't really care. So that's what this last statement is saying. It's not so much saying that this convergence never occurs. It's just saying that it only occurs on a set of measures 0. Thus, it effectively isn't happening, right? Thus, we don't have this Sn over n converging to a finite value. So it's like contradiction. Therefore, this sum can't, or this Sn divided by n can't converge to a finite value. For example, think of the Cauchy distribution, which does horrible things if you try to do a law of large numbers on it. We can do that just for fun at the very end. I should just switch over to RStudio, and that'll be kind of amusing. Anyway, the hard part's actually proving part 1. And we're going to use similar arguments, though, like the sums of probabilities in Borel-Cantelli. I mean, ultimately, what we'd kind of want to do is use Chebyshev's inequality, but the problem is that we don't have a finite second moment, or we're not assuming the second moment is finite, so we can't immediately use Chebyshev. But now what we do is we can kind of make it, we can achieve a finite variance by bounding things in just the right way. So first, we assume that the expected value of xi is equal to c, and this is some real value. So what we're going to say is, without loss of generality, w log xi is going to be greater than or equal to 0 for all I. So why can we do that? Well, else write x as equal to x plus minus x minus, minus, and do everything for x plus and x minus as positive, non-negative random variables. Also, independence of, say, x and y implies independence of x plus and y plus, and similarly for minus and minus. And I think I just left that as, like, you can check that. I say check for any measurable functions. X and y are independent implies that f of x and f of g and g of y are independent. So the point is, if you have two independent random variables, and you apply a measurable function to each of them, it could be different functions, then the output would still be independent. So independence is kind of a nice thing that you can kind of maintain across messing around with your random variables. But we'll leave that for independent investigation, which means I'm too lazy to write it all out in detail and just want to get on with the proof. Also, to continue our alsos, F denotes the law or distribution of x, i.e., f of little x is going to be the probability of x, big X, being less than or equal to little x. This is the distribution function, which I'm guessing you're familiar with. Again, we can still think of this in this measure theory context where x is a measurable function and this measure is happening on omega. But in the end, capital F is just going to be a distribution function. Going to look like a little S-curve, kind of like what we would get from like a Gaussian or whatever you want it to be, right? Doesn't have to be Gaussian. I just always default to thinking in Gaussians. All right, so that's the setup. Now, what in the world do we do? Well, first, we define yi to be xi indicator function xi less than or equal to I. So remember, we're assuming that all the xi's are non-negative. And now what we're doing is we're creating a yi that kind of cuts off xi. It's xi until xi gets kind of big, then it just gets set to 0. So we're truncating it in some way. You can think of it like if I had a normal distribution bell curve and I kind of cut off the tails, so now it's bounded. So we define y like this, and we define Tn to be the sum I from 1 to n of yi. So again, this is kind of like we started with xi and sn, and now we have yi and tn, which are kind of the truncated versions of xi and sn. The point being is that if I have a bounded random variable, now I'm going to have a finite variance. So what we want to do is we want to do Chebyshev applied to the y's and the tn, much like we did for the weak law, where we could apply it to sn, but the weak law assumed a finite variance. So in this case, we're kind of forcing a finite variance into the equation. So for any delta greater than 1, we can define, this is kind of an annoying bit of this proof, so let's go through it a little carefully, right? We can define a non-decreasing, decreasing integer sequence, which is going to be kn, and kn is going to be the floor of delta to the n. Right, so if you want to imagine what that is, right, delta to the n, delta is going to be greater than 1, which means we have some kind of a exponentially growing delta, right, delta, maybe I'll write it on the other side because I need to do a floor in a second, delta to the n. And then what we're getting here is that for n, let's say 1, 2, 3, 4, 5, 6, then, right, what kn is going to be is it's going to be the floor of this. It's going to be, well, I guess that's not really the floor. The floor would be if I had integers going up here, where this would be 1 and maybe 2, 3, 4, 5 or so. Then what I would do is find, well, the smallest integer that is below the line. So I might stay down here and then kind of go up. So I'm creating an integer sequence, but it has to lie below this curve, right? That's what the floor is doing. It's not immediately obvious why we're doing this yet, but we need this sequence for our what's to come. So this sequence has some nice properties to it. We'll say then, given this sequence, we know that, well, 1 is a lower bound for kn, and kn being the floor has to be less than or equal to delta n. Again, because it's the floor, it has to be strictly less than kn plus 1. And kn plus 1, because kn has to be greater than or equal to 1, is going to be less than or equal to 2 times kn. So again, we're going to need all these little tidbits in what's to come, which is why we're writing them down. So maybe we'll put a little bullet point here so we don't lose it in the notebook. So we got that bullet point. We also have that if we believe it, that kn to the minus 2 is less than or equal to 4 delta to the minus 2n. Why would that be true? Well, we can use the previous one, right? We can replace n, well, we can square this and square this guy, and we get a 4kn squared and a delta to the 2n, then we just divide everything by the kn squared and the delta 2n to get that. And we have another one. There is a reason why we're doing all this, so just stick with me a little longer, right? Also, if I sum n from 1 to infinity, also I should point out that nobody actually the first time someone ever proved this, they didn't go through and just write all this down, right? We're writing it down like this to kind of get the tools we need to do this giant derivation that's about to come. Of course, what probably happened is if somebody was working through this derivation, they would get to these different sticking points and say, okay, how do I get from line 4 to 5 and 5 to 6? I'm going to have to get one of these blue dot formula to get me through it. The way that we present proofs and the way that people probably develop proofs, it's not always the same, right? It's sometimes I assume it's like almost the exact opposite. Like we present it in one way, but it was probably proved in reverse. But nevertheless, this is probably the clearest way, hopefully, to present this. The clearest way I can come up with. All right, so we have this crazy thing here. Let me write it down, then we can stare at it and see if it makes any sense at all, or if we want to just kind of like believe it and move on. Indicator. I need to be very careful that I don't mess up any of these symbols. 4 divided by I squared, where here I is an index, of course. I think in the next lecture when we do the central limit theorem, we're going to need complex numbers for characteristic functions. So then I is going to actually be the square root of -1, but not today. Oh yeah, I forgot. And this proof also has a whole bunch of constants. C0, C1, C2, etc., which is all the junk that we really just don't care about, and we shove it into the constant so we don't have to look at it. Anyway, what do we have in this crazy line here? And this is for some C0 greater than 0. The specific value of it, don't really care what it is, so we're not going to worry about that. Right, so what we're doing here is we're summing the 1 over kn squared, n from 1 to infinity, but we're also multiplying by this indicator function that says kn has to be greater than or equal to I. Well, using the previous blue dot, we can move from the first line here, or the first thing, to the second thing, which is where we replace kn to the -2 with 4 delta to the -2n. Nothing changes. Well, now we have something that looks like a geometric series, almost, right? Which is where we're going to get this result here. But, and the 4 just carries over, but we're starting it for, we're only summing it if once delta gets greater than I, delta to the n gets greater than I. So we're kind of starting it a little bit late, which is where this like I over 2, 1 over, well, I to the -2, or I squared in the denominator comes from. And then the point being that we don't really care what delta is. Delta is just some number. So 4 divided by 1 minus delta to the -2 becomes C0. It's just something. We don't care what that something is. We just care that it's a constant and it's positive. And we're going to move on from there. Oh, another thing to note. Yeah, this is just like the worst, right? It's like, let's just write down a bunch of equations that don't immediately have any meaning at all. Well, if we sum I from k plus 1 to infinity, k is probably a bad choice, actually, because kn, well, I guess I'm going to use k later. We'll use k. K is not kn. K is an index. I to the -2. So if we sum up this thing, right, what we're doing is we're kind of, in some sense, doing an integral k to infinity of x to the -2 dx. We can just like Riemann integral it, not have to worry about Lebesgue in this case. And if we solve that integral, we know that the value is 1 divided by k. Again, if you want to see why that inequality should hold, right, just imagine the function x to the -2, right, which is going to kind of curve down like this, and we're going to be sticking below it. We're kind of like doing a lower, like a lower Riemann sum with this I to the -2 here that we're summing up from k plus 1 to infinity. So that's roughly what's going on there. Anyway, we got all the crazy stuff, so now applying, well, I'll tell you where we apply Chebyshev's inequality. Now we'll say for any t greater than 0, there exists a C1 greater than 0, depending only on t and delta, such that the probability, here we go, let's do this, the sum n from 1 to infinity of the probability that t kn minus the expected value of t kn is greater than t times kn is going to be less than or equal to some constant. Don't care what it is, just care that it only depends on t and delta. We're applying Chebyshev, I guess, an infinite number of times here for n from 1 to infinity. Kn minus 2 variance tkn. So this Chebyshev applied to each of these probabilities in the sum. The reason why we're starting with this infinite sum is that we want to use Borel-Cantelli. We want to show that, I guess this is going to have a finite value. Let me get to the bottom. Yeah, we want to show that this sum, the thing that we're starting with, is going to have a finite value. Then Borel-Cantelli is going to tell us that, well, that means this thing can't occur infinitely often, right? So as a result, it's going to tell us that we get some type of convergence, almost sure convergence for the TKN series sequence, the sequence of TKNs as n goes to infinity. But we have to show that this thing is finite, and it's going to take us 8 lines to do that. So the first line is apply Chebyshev and bound each of these probabilities by the variance divided by k squared here. And again, the t and everything else can just get wrapped up in c. C we don't care about. As long as it has nothing to do with n, we can take it out of the summation. Right. So we got that. Well, now let's see how we can fight our way through this. So I'm going to give myself more room. But we're going to go down the... Oh, no, this is not an inequality. This is equal. So what we're going to do is just rewrite the variance. So we're going to go n from 1 to infinity, and we're going to rewrite the variance of tkn as the sum of the variance of the yi's. We can do this because of independence. I mean, I guess uncorrelatedness in this case. We should pay attention to when independence shows up in the proof, just to show that it's necessary in this proof. Okay, so this is just by decomposing the variance of tkn into the sum of the variances of the yi's. Now we're going to flip the order of summation. C1 just sits out front, doesn't do anything. We're going to get I from 1 to infinity of the variance of the yi, and for each variance yi, what we're going to get is a sum, an inner sum, right? If you think about this, right? I'll do a big square bracket. This is going to be the sum, and then this summation index is kind of weird, but it's all the kn that are greater than or equal to I, 1 over kn squared. So that one might take a second to stare at, but in some sense, the previous sum that we were looking at, right, is going to be n from 1 to infinity, and for each n, we're going to get a kn squared in the denominator, and then we're going to sum a bunch of variances. Well, now, if we kind of flip it, right, for each of those variances of yi, we're going to have some infinite collection of 1 over kn squared summed up. And that's exactly what we get here. So the reason we do this is so that we can then, if you kind of stare at this thing, say, well, wait, didn't we see something like that? Oh yeah, we did. It's kind of up here, right? That's this thing. Yeah, so that's what that is, and why we did this kind of goofy derivation, because we want this guy on the right-hand side. But luckily, it hasn't fallen off the top of the screen yet, so I can show it simultaneously. And what we get is that this thing, less than or equal to, I feel like there's a typo here, that should be squared. Should be C2, which is all the stuff I don't care about. Has nothing to do with i's and n's, and then we sum I from 1 to infinity of the variance of, nope, not that line. Next line, which is I to the minus 2 power, which is precisely where I put that arrow up there in the top right, and we need an expected value of yi, but I think it should be yi squared. In my notes, I put yi just without a square, but that doesn't seem right. Because the variance, which is kind of the centered second moment, right, is should be bounded above by just the second moment. So I'm going to assume, yeah, no, because the next line, this does make more sense. Yeah, anyway, we have this, thanks to that equation up here. Then we're going to drop our expected value notation. Maybe I'll just write this note. The variance, yi, less than or equal to expected value, yi squared. Which can be done by like solving least squares and stuff. Anyway, what we get now is we're going to keep everything the same, but we're going to rewrite this expected value in terms of an integral. And the integral, remember, what is yi? Like, let's go back and look, right? Yi is going to be xi, but truncated, so it can't go any bigger than the value I. So what that means is we're going to go from 0 up to I, x squared dfx. So we're taking the expected value of x in some sense, but only for the finite interval 0 to I. Recall that x is assumed to be non-negative, thus y is also going to be non-negative, but y is bounded. Now what we do is we break this into pieces. I from 1 to infinity. We're going to have I to the minus 2. And then we're going to sum up a bunch of stuff. K from 0 to I minus 1 of the integral k to k plus 1 x squared dfx. Told you the strong law of large numbers is so much worse than the weak law, right? Okay, what did we do there? Well, we just took 0 to I and we cut it into a bunch of integer pieces. So there's nothing too profound going there. We just cut up an integral into a bunch of little pieces. What is more interesting, maybe not, we'll see. Well, what we can do, right, is we can upper bound this by a new constant. So every time I change the index, C1, C2, C3, I'm getting a new constant, which means I'm shoving more stuff I don't care about into it, because otherwise there'd be all these extra terms that really don't matter one bit. Anyway, in this case, what we're doing is we're, in some sense, switching the order of summation again. We're taking each of these k's from 0 to infinity, and then we're getting 1 over k plus 1. The integral k plus 1 x squared df x. Yeah, which is really just noting that if I fix a k and I sum over all the i's, I'm going to get some number, right? I think the sum of I to the minus 2 from 1 to infinity is going to be something like, isn't it something like pi squared over 6 or some crazy value? I have to call up Rob Monajan and ask him because I'm not sure. But whatever it is, it's finite. And every time we do one of these sums, we're going to get some goofy number. Doesn't really matter what it is. It just matters that it's not dependent again on like what I or k, or I disappears here, or k, I guess. So we can pull the whole thing out of the equation and change C2 to C3. Lastly, then what we're going to do is we are going to upper bound this thing by C3, sum k from 0 to infinity. And then the question is, well, what do we do here? Well, we can actually upper bound this. And again, typo on my part. I'm being a little sloppy here. I lost the integral sign. X df x. And the question is, well, why am I allowed to do that? Oh, and this should be from... I guess I just, deleted the... Why would this be the case, right? Well, this is because if we note, I guess I can keep this as k plus 1. I didn't actually include that in here in my notes, but the point being that in here, right, we have k less than or equal to x less than or equal to k plus 1. Therefore, x divided by k plus 1 has to be less than or equal to 1. So in some sense, I'm taking the k plus 1 and one of these x's, and I'm upper bounding it with a value of 1, which means the whole thing kind of vanishes, and I'm left with just an integral of this. And this integral looks almost like the expected value. In fact, I think that's right. I think what I did it in one step, which kind of made it slightly less clear. But in this case, right, we can upper bound this by the sum k from 0 to infinity of the expected value of xi. Doesn't matter what the I is. They're all the same, right? And this is finite by assumption. So, why in the world did we do all this? The whole point was to get that this original thing at the top here had a finite sum when we take n from 1 to infinity. Why did we pick this crazy value for kn? Well, we needed it so that we could get this bound in the way that things would work, right? You could go back through this and see, well, what happens if kn is just equal to n or something, right? Then you're going to have some trouble moving, say, from moving from some of these lines, right? Because, for example, this first inequality shows up when we use this crazy bound up here, right? Which happens just because of how kn is related to delta to the n. So, we need the sequence of integers kn to increase at this somewhat exponential rate so that we can get this thing to work the way we want it to work. I mean, there might be other ways to do it, but this is the way that I saw people in the textbooks doing it. Anyway, in the end, what do we have? We have that the sum n from 1 to infinity of the probability of t kn minus t, or expected value of t kn being greater than t times kn is finite. What does Borel-Cantelli tell us? Well, basically, BC says that this thing, we'll say 1 over kn tkn minus the expected value of tkn goes to 0 almost surely. If we recall Borel-Cantelli, right, it says that if this thing is finite, then the set of where this inequality holds true infinitely often will have a measure of 0, which means in some sense for almost all omega, tkn minus the expected value of tkn will eventually be less than this value t times little t times kn. And that's precisely what we mean by almost sure convergence, right? For almost all omega, this thing is going to go to 0. So the way I often think of Borel-Cantelli is if I have something that converges in probability by like Chebyshev or otherwise, if it converges in probability fast enough such that this sum is finite, then I can bump up my probability convergence to almost sure convergence. So if you want to show that something converges almost surely, yeah, Borel-Cantelli is a nice way to do it. Anyway, we're not done yet. We just basically showed that we have almost sure convergence for the bounded tkn, but not for Sn yet, which is what we actually want. So next we say is since the expected value of yn increases to the expected value of xi, where whatever I doesn't really matter, we have, right, because as n increases, right, the bound becomes weaker and weaker, but all the x's have the same mean. So anyway, we have that kn inverse expected value of tkn is going to also monotonically increase to the expected value of xi, again, as these are both as n goes to infinity. So, okay, what do we have here? Well, we have that this almost sure convergence holds, and this guy converges to the expected value of xi. This is, remember, in this case, it's the expected value of tkn converging to the expected value of xi. So this is just a convergence of a monotonically increasing sequence of real values, right? We're not dealing, these convergences here, they're not probabilistic convergences on the second line. This is just sequences of real values. So put this all together, and what we get is that, therefore, kn inverse tk, a random variable sequence, will converge almost surely to the expected value of xi. So we know that our truncated tkn will in some sense satisfy the strong law of large numbers. That is, we get almost sure convergence. And now we just need to figure out how to get back to Sn. So to get back to Sn, note that note that since, it's not so much an if, I guess I just used x. All right. Note that, we'll say, we'll get there, right? Just trying to make the English some semi-coherent. Note that for a random variable x such that the expected value of x is finite, or for a random variable x, the expected value of x is finite. This is if and only if the sum I from 0 to infinity p x greater than I is finite. this is something again that we used this this same idea up in the first part of this proof. Now, yeah, I said not gonna. You can find proofs of this in textbooks if you're interested, but I'll just say not use the curly brackets because I need the curly brackets in a second. Footnote is consider sets of like I, k equal to all of the k, or yeah, k less than x. I said less than equal to x plus 1, but that seems a little confusing. I feel like what I meant to say was k plus 1. The point is, you can try to show this if you want, or you can find one of the proofs in one of the many textbooks. I just don't really feel like going through all of it right here. But yeah, if we believe that, right, if we believe that a finite expectation is if and only if this sum of probabilities is finite, then the sum I from 1 to infinity of the probability measure that I is not equal, xi is not equal to yi. Well, what is that, right? This is the set of omega where these two measurable functions do not coincide. That is, where xi omega is not the same as yi omega. Again, it almost makes more sense when you think of these as functions rather than as like whatever a random variable is outside of the measure theory context. Anyway, this is just that, right? The probability. So the probability that xi is not equal to yi, that occurs only for omega that make xi greater than I. Because if xi is greater than I, then xi is just xi, but yi gets set to 0, so the two will not coincide. Otherwise, the two coincide. And this is finite. So Borel-Cantelli, thus, this is finite, right, because of this expected value, right? Just to like make it really clear, right? This thing is finite because of this line that I wrote up here. And then we go back to BC says, Borel-Cantelli tells us that the probability measure of the lim soup, if we use that notation, of xi not equal to yi is going to be 0 for, yeah, hence it basically means that in the limit, right, these things cannot be different infinitely often. So again, the set of omega such that these two things differ will forever, right, will have measure 0. Hence, for I large enough, right, this doesn't occur infinitely often, which means there's a big enough I such that xi is going to equal yi almost surely. And so on, I guess, for all I large enough. So that's what this is telling us, right? And it's how we can kind of, because I feel like the first time you see like a lim soup of something, it's not always clear like what that exactly means. But in this case, what we're saying is that eventually these things can't not be equal to each other, except on a set of measure 0. So what we're really saying is eventually there will be i's large enough such that xi will equal yi almost surely. So let large enough mean all I greater than m omega. So the point is that we can actually consider that there exists an m, right? But it's going to depend on omega, where the point being is, i.e., I'll just put i.e. xi omega is equal to yi omega for all I greater than m omega. Right, the two functions coincide now. The two sequences of functions, xi, I going off to infinity, yi, I going off to infinity, will eventually coincide for large enough I. Almost surely. Gotta love this stuff. Anyway, we'll say, furthermore, k n inverse s m omega is going to go to 0, of course, because right, because in this case we're just saying sm, so that's fixed, a fixed summation divided by this number that keeps getting bigger, kn, is going to go to 0, and kn inverse t m omega is going to go to 0 as well, as n goes to infinity. And what does that mean? So therefore, the terms, that is, the first m terms in the sum, where xi and yi do not coincide, become negligible as n goes to infinity. So that's what we're intuitively saying here. We're saying that Sn is the sum of the first n terms. If we take the first m of those in the limit, we don't really care what the first m are, because they're going to be divided by a bigger and bigger and bigger number, and that part's not going to matter anymore. It's only going to matter what happens in the limit. In the limit, xi and yi will coincide, almost surely. Almost there. Therefore, what this means is that kn, or to the inverse, skn is going to converge almost surely to the expected value of xi. So, therefore, we have almost sure convergence for a subsequence. Oh, so close, right? We wanted almost sure convergence for Sn divided by n. We got Skn divided by Kn, so almost there. Now we just need to take delta to 0, or sorry, delta to, not to 0, delta to 1. I wrote to 0, but I think this section is probably full of typos because I was probably really tired when I wrote it out. Luckily, I can correct it in real time, but if you read it, there might be some typos I need to correct. Finally. All right, so finally, what do we do? Well, the last bit isn't so bad. We know that kn plus 1 divided by kn is going to converge to delta as n goes to infinity, right? Kn is just the floor of delta to the n, so we basically have the floor of delta to the n plus 1 divided by delta to the n. Eventually, delta to the n is going to get so big that this thing will just converge. Therefore, right, there exists an n large enough. There exists an n large enough such that 1 is less than or equal to, let's do a better 1. 1 is less than or equal to kn plus 1 over kn, and this is strictly less than delta squared, right? Because eventually kn plus 1 over n is going to be really, really close to delta. Delta is greater than 1, so delta squared is greater than delta. Thus, for kn less than I less than kn plus 1, what we get is we get that skn over kn, the subsequence, is going to be less than or equal to delta squared si divided by I by this relation here. Yeah, because of the way that if we, this is less than or equal to delta to the fourth skn plus 1 over kn plus 1. Okay, so you see we're going to kind of squeeze it in here, right? Because now what we can do is do a little bit better and note that delta to the minus 2 expected value of xi is less than or equal to the lim inf I going to infinity of our sequence si over I, which is less than or equal to, of course, the lim sup. We want these two things to coincide so we get our limit. I kind of like this end of the proof because it kind of gives you an idea of what's going on with subsequences versus sequences. xi. So thus, take delta to 1 and QED. So what's going on here, right? Well, what we're basically saying is that the sequence that we are interested in is going to be bounded above and below by skn over nkn times either delta or delta squared or delta to the minus 2. Thus, we know that the guy on the left is going to converge almost surely to the mean. The guy on the right is going to converge almost surely to the mean. Now, the thing in between, we don't know yet if si over I converges, but the lim inf and the lim sup have to exist. By this line, we know that the lim inf has to be greater than the expected value of I times delta divided by delta squared, and we know that from the other side, that the lim sup has to be less than or equal to the expected value times delta squared. So we don't have it done yet, but delta was arbitrary, right? It was just some arbitrary value greater than 1. As we take delta down to 1, we squeeze the lim inf and the lim sup together. Lim sup is equal to lim inf is equal to the expected value of xi, and we're done. We get our almost sure convergence. Good stuff, right? Yeah, I love this stuff. Anyway, yeah, I think that's pretty good for the lecture for today. In the next lecture, we'll be talking about the central limit theorem, which is a whole nother thing. But stay tuned, because I'm going to switch over to RStudio, and I'm just going to show you some pictures to show you what this convergence looks like, because it's fun. I really like looking at pictures. All right, welcome to RStudio. We're just going to do a real quick fun stuff to see if this actually works. So I'm going to say, let's say, well, for lack of a better variable name, we're just going to call it xx1, which is going to be random normals, and we'll take this out to like 500 standard mean 0, covariance or variance 1, normals. Let's plot that and see what happens. We're not going to plot it, right? We're going to plot the cumulative sum, cum sum, of xxi, xx1. And we're going to put this on a, well, let's plot it like this and say type is equal to L. So what is happening? Well, we plotted the cumulative sum, which is a random walk. This is effectively the Sn that we had in our proof, right? It wanders around. But what would happen if we took this whole thing and divided it by 1 to 500? Which means that we are now getting Sn divided by n. Well, now it looks like it's going to 0 pretty fast, right? What we can do is we can give ourselves, we can do one thing better. We can give ourselves an AB align and say h is 0, the mean, and the color can be, I don't know what color you like to look at, but let's do red. We'll do LWD as 2 or 3. So there's our 0. So, we're kind of tending towards it, 500. It actually didn't go as fast as I expected it to go, but I guess we could get those Berry-Esseen bounds if we really wanted to, but I forget what the formula looks like for those. We can also take this out if we just, let's go back here and take this out to something crazy like 10,000 and see if we can not break my poor little laptop here, which is getting quite old at this point. Oh. Because I didn't change this. I was like, well, that doesn't look right at all. It doesn't look right because I'm still dividing it by 1 to 500 and R just wraps it. There we go. Now we're really converging. If we really want, we can look at this, I guess, on like a log. I don't think that would be that interesting. We can try and look at it at a log scale and see if it's interesting. I guess that's kind of interesting. Here we have the log scale, right? So we can see how our Sn divided by n is going down to 0, and that's, I guess, almost sure convergence for you. But what's really cool is that this is the normal distribution, right? The Gaussian. It has all of its moments are finite. But maybe what we can do is we can go back to my x2. And now I'm in my old code, because RStudio just saves everything. We could do a random t distribution, where our t distribution is going to have degrees of freedom equal to 2. So if we have a t distribution with 2 degrees of freedom, we now have infinite variance, but a finite mean of 0. So let's see. Does the theorem actually hold up, or are we just completely lying to ourselves? Yeah, we got it. Look at that. So notice that it does fluctuate a bit, but it does still go back to 0 in the long run. At least by the time we get above like 1,000, maybe 5,000, up to 10,000, we're getting pretty close. I guess in contrast, the normal ones seem to calm down a little bit faster, which makes sense, right? But even having a distribution that has an infinite variance, we still get that nice convergence. Almost surely. I guess what would happen, though? Let's see, though. Can we push it even further, right? Because our theorem also claimed that if we have something with an infinite variance... Where is x3? There we go. If we have something that has not infinite variance, an infinite absolute... first absolute moment, then this should fail. It shouldn't converge to anything. So if we change the degrees of freedom to 1, we now have the dreaded Cauchy distribution, which has no definable moments, I guess. What happens when we plug this in? It keeps bouncing around. It actually doesn't like bounce around as crazy as you would think, but notice how it kind of like starts to go down to 0 and then suddenly jumps up, and then it kind of goes down and jumps down. And if we took this out even further, presumably it would just keep jumping. I wonder if we can do this out to 100,000, or if my computer's going to get mad at me. Yeah, there we go. Notice how it just continues to jump around quite chaotically, even as we go out to n is equal to 10 or 100,000. So this is kind of the failure of the law of large numbers to hold if we do not have a finite first moment, such as in this case, where the first moment is undefined, infinite in the absolute case. Cool. I just love looking at these pictures, so I thought it would be fun to do that before we sign off for today. But that is all I wanted to talk about. Thanks so much for listening. Next time we'll be doing the central limit theorem, which means lots more random variable convergence. Central limit theorem is not as tedious with respect to the computation we have to do, all of this bounding and sequences, but we're going to need characteristic functions and some stuff to talk about convergence of measure and convergence in distribution. So that should be kind of fun. See you in that one.